we already know what an arithmetic sequence is by now. So what is a geometric sequence? Well, if an arithmetic sequence is a sequence that has what's called a common difference, or another way of saying that we're adding the same value every single time, a geometric sequence is one in which we have what's called a common ratio, or we are multiplying each term by the same value every single time to get the next term. That's called a common ratio. So if we take a look at this particular sequence that we have here, what would our common ratio be? Well, it's pretty evident that our common ratio is 2. In other words, we're multiplying by 2 every single time, right? So from 2 to 12, we're multiplying by 2, right? So we would say that our common ratio is 2. Now, that's easy and all. And if I wanted to find the next term, I could easily just multiply 48 by 2 to get the next term. The issue here is I want an efficient way of being able to determine any term in this series. So if I asked you for the 72nd term in this particular sequence, it would be really annoying to have to continue to multiply by 2 every single time. So in order for me to think about an efficient way of determining any term in this sequence, let me actually go ahead and rewrite these terms. Let's do this in another way. So we know that our common ratio is 2. We're multiplying every term by 2. So one way that I'm going to, again, think about this is say, all right, my first term in my sequence is 3. And ask myself, how many times have I multiplied 3 by 2? And the answer is 0 times. I haven't multiplied it by 2 yet. Well, the next term, 6, I start out with 3. And again, how many times have I multiplied this 3 value, my first term, by 2? And the answer is once. Now 12. If we start it with in the context of thinking about it from the first term, again, 3 times my common ratio 2, 2 times. So you kind of see where this is going. I'm multiplying 3 by 2 3 times, and I've now got 4 instances of 2 to get 48. Now, why am I writing it this way? Because I want to kind of highlight what do we know and how can we use what we know to come up with a general formula or an nth term. Well, we seem to be able to say the following, that our a sub n, our general term, is going to be determined by taking our first term in our sequence, a sub 1, right, a sub 1, times our common ratio, and what is our power going to be? Well, our power is always going to be that order number minus 1, right? So for this term here, this was the 5th term, this was a sub 5, and I see that my degree here is 5 minus 1. So we can just generalize this and say this is our nth term formula for a geometric sequence. And another way of writing that is what I have over here, right? Which is simply saying, okay, well, we don't always have to start with the first term in our sequence. We can use any term in the sequence and rewrite the nth term that way. And one last thing that I want to just highlight before I go into some practice problems, if we think back to arithmetic sequences, like for example, something like 2n plus 1, what I mentioned in our previous lesson was that this could be thought of as a linear function, right? If we were to graph these terms, it would form a line. Well, what about for a geometric sequence then? What are we seeing here? We're seeing that this would clearly be an exponential function, right? We're taking some ratio and we're raising it to some power. And so we're going to experience exponential growth. All right, let's try a couple practice problems now. So let's start with this first sequence, and there is a typo there. I apologize. Here we go. Let's just remove that. There should be negative 4 root 3. So let's look at this first sequence here. So let's come up with the formula of the nth term. And this is going to be pretty straightforward. First off, what is our first term? Our first term, a sub 1, is 4. Next, what is my common ratio? What am I multiplying by every single time? And an easy way to do this is just to take the second term and divide it by the first term. So negative 4 root 3 divided by my first term, 4, and I get negative root 3. So that's all I need to be able to write my nth term of this geometric sequence. I can say that a sub n is equal to a sub 1, which is 4, times my common ratio, and that raised to the n minus 1 power. Now let's try another sequence where this time we're not given the first term. In fact, we're only given 2 terms in this sequence. And the first thing we're going to want to do is we're going to need to figure out what is my common ratio here. So I'm going to use my a sub n here. I'm going to use my a sub n is equal to a sub m times r to the n minus m. And it doesn't really matter which one we choose for our a sub n or a sub m, but I'm going to say let this be our a sub n. Okay, let's just let this be our a sub n, and this here be our a sub m. And let's plug this into our nth term formula and see what we get. So we have 81 over 80 is equal to 1 over 5, and it's our common ratio that we're trying to solve for. And what is the difference in order between 3 and 7? It would be 7 minus 3. So using some basic algebra, I'm just going to multiply both sides by 5. So 81 over 80 times 5 is equal r to the fourth. So 5 goes into 80 16 times. So r to the fourth is equal to 81 over 16. Now, if I want to solve for r now, we can just go ahead and take the fourth root of each side. And then r is equal to 3 over 2. Now, before we move any further, ask yourself, have I missed anything here? And the answer is a resounding yes. Anytime I'm taking an even root, I've got to make sure I consider the plus or minus. So think about the implications of this. What we're saying here is our common ratio could be positive or negative. Given the fact that we're given only the even number terms, there is a possibility that my common ratio could be negative 3 over 2. I could be multiplying by negative 3 halves. You just can't see it based on the information that's given. So whenever we're taking an even root degree here, we've got to consider the possibility of a negative ratio. So we would say r is equal to plus or minus 3 halves. Now, the next thing I want to do is I want to go ahead and solve for a sub 1. So let's find a sub 1. So find a sub 1 here. So what is a sub 1? So to find a sub 1, I'm going to, again, use my nth term sequence or nth term formula. So my first term that I'm using is a sub 3, so that's 1 over 5. We said our common ratio was negative 3 halves, or plus or minus 3 halves, excuse me. And what was the difference in order? It's n, in this case, I'm solving for the first, minus m, which was 1/5, which was 3. 1/5 was the third term. So a sub 1 is equal to 1/5. We got plus or minus 3 halves to the negative 2 power. And when we're raising something to the negative 2 power, that's equivalent to multiplying that reciprocal, or excuse me, taking that reciprocal to the positive 2 power. So if I just simplify this, this is going to give me 1/5 times 4, so that's 4. 5 times 3 to the second power, so that's going to be 45. And that positive, the fact that I'm taking this to the second power is going to take care of that plus or minus. So I'm able to determine that my first term must be positive 4/5. So if I want to put it all together to come up with my a sub n, let's write that here. So we'd say a sub n then is equal to my first term, 4 over 45, times my common ratio, plus or minus 3 halves, raised to the n minus 1. So there's my general term, or my nth term, I should say. All right, now let's move on to talking about a geometric series. Well, again, a geometric series is simply when we are adding the terms of a geometric sequence. What we have here is the formula to find the sum of a geometric sequence, and it's simply the first term that you're adding times 1 minus your common ratio raised to the n power, and again, n is going to represent the number of terms that you are adding, okay, all over 1 minus r. So let's do a basic example with this. So we've got a geometric series where our lower index is 1, our upper index is 5, meaning we're starting with the first term and adding all the way up to the fifth term. We can say that our common ratio is negative 1/2. So what we do need to find is a sub 1. Now at first glance you might be tempted to just say that it's 16, but look at it carefully. A sub 1 is going to be equal to the following. We're going to say 16 times negative 1/2. Again, this is our a sub n. This is our formula for generating the terms in a sequence. So we're going to say 16 times negative 1/2 raised to the first power. And that's just going to give us negative 8. Well, our common ratio is negative 1/2. And so we can go ahead and now find the sum. Let's do this in a different color. We can find the sum of the first 5 terms in this series using this formula. a sub 1 is negative 8. Okay. We can then say 1 minus our common ratio, which is negative 1/2, raised to the 5th power, all of this over 1 minus negative 1/2. Now, from here, it's just going to be some simplifying, so let's go ahead and work through that. So we've got negative 8. We know that negative 1/2 raised to the 5th power is going to be negative 1 over 32. So since I'm subtracting a negative number, I'm going to say 1 plus 1 over 32. And all of this is over 3/2, which now I'm going to say negative 8 times 33 over 32 times 2/3. Okay, just some basic simplifying rules. So let's just go ahead and clean this up. 3 goes into 33 11 times. 8 goes into 32 4 times, and 2 goes into 4 twice. So no, that looks a little messy, but that's just going to simplify cleanly out to negative 11 over 2. So here is the sum of this geometric series. Okay. All right. I'm going to go ahead and encourage you to try this next one on your own. So pause the video and give this next problem a shot. Well, if you had a chance to work through it, we can establish a couple things. First off, a sub 1 is equal to 15. Our common ratio is our second term divided by first term, so negative 3 over 15, which is just negative 1/5. What eludes us right now at first glance is what order number is this? Okay, what term is negative 3 over 625? So let's solve for that. So we'd say, all right, negative 3 over 625 is equal to, using our nth term formula, 15 times negative 1/5 to the n minus 1 power. And what we're looking for is we're trying to figure out what is n. We've got everything else. We just need to know what order number was negative 3 over 625. So we're just going to use some basic algebra for this. We're going to divide both sides by 15. So that's going to simplify out to negative 1/5. I apologize, 331/25. Okay, that's what that's going to be, is equal to negative 1/5 to the n minus 1. Now, since our numerators are going to be negative 1 in both cases, what we're really just concerned with is 5 to what power is 3,125? And the answer is, we would say, to the 5th power. But again, we're asking ourselves what n is. So in other words, what we know is the following. We can say, all right, I know that negative 1/5 to the 6th power gives me negative 1 over 31/25. But since my degrees have to be the same, since I know those degrees have to be the same, I can say that n minus 1 is equal to 6. N has to be equal to, I apologize, this one back here should be 5. I wrote 6. I got a little ahead of myself. So since I know that n minus 1 has to be equal to 5, I can say n is equal to 6. Well, if that's the case, now I can finally write this in sigma notation. I can say, I start with n is equal to 1. I end with n being equal to 6. And so that solves that mystery. I know that this was our 6th term in our series. And our nth term is just 15 times negative 1/5 raised to the n minus 1 power. So that is this same series just written now in sigma notation. Okay. Now, finally, I just want to close by looking at the sum of an infinite geometric series. Well, let me kind of start off by giving you two different geometric series. Let's say, for example, I have the following geometric series. It said 1 plus 2 plus 4 plus 8 plus 16 plus 32. So something like this, my common ratio is what? R is equal to 2. Now, pause the video and ask yourself the following question. Can I find the sum of this infinite geometric series? Can I find the sum of this infinite geometric series? And the answer is clearly no, right? The sum never seems to settle on to a finite value. It's just going to continue to grow. Now, let me give you another geometric series, something like 1 plus 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1 over 32. Now, how about for this one? Does this series look like it will have a finite sum? And the answer is yes. It appears that as the number of terms approach infinity, the terms are starting to get really, really small. right? Our denominators we're seeing are doubling in size and in value. So effectively what we're doing is we're adding terms that are 1 over a very large quantity, which effectively is 0. It approaches 0. So after a while, you're adding terms that approach 0 in value. So your entire sum of this infinite series isn't going to change. Now, what was the ratio of this geometric series? Well, r this time was equal to 1/2. So what was the difference between the two? And the answer is it has to do with that common ratio. The fact that our common ratio here, in this case, in the second series, is a value that is less than 1. Its absolute value is less than 1, which is what I want to highlight here. So that's where we can draw a more general and broader conclusion here. We can say that if the absolute value of our common ratio is less than 1, then our series will have a sum. Our infinite geometric series will have a sum. If the absolute value of our common ratio is not less than 1, then we're going to have an instance where our sum continues to grow or decrease towards some negative infinity value. So if the absolute value of our common ratio is less than 1, then we can find the sum of an infinite geometric series. So if we take the same formula that we use to find the sum of an infinite geometric or of a geometric series, think about what happens when our n value, which again is the number of terms, when our n value is infinity. If you take a fractional values, for example, 1/2 and raise it to the infinity power, that's equivalent to 1 over 2 to the infinity, right? And so again, that denominator is going to continue to grow, which makes this entire ratio, as we raise this fraction to infinity power, that's going to make this get closer and closer to 0. And when you have 1 minus 0, that's just 1. And what is 1 times a sub 1? It's just a sub 1. So we have this formula here. So let's go ahead and try the same geometric series that we looked at earlier. Actually, yeah, it is the same exact geometric series, but this time let's make it an infinite geometric series, and let's see what the sum of that series is. Well, first off, what is a sub 1? We said earlier that a sub 1 was equal to negative 8. And what did we say our common ratio was? Negative 1/2. So let's find the sum of this series. The sum here of this series would be a sub 1, negative 8, all over 1 minus negative 1/2, which is just negative 8 over 3/2, and all of this is negative 16 over 3. Okay? And go ahead and try this next problem on your own. A hint that I can give you is to look at something like this and recognize that it is equivalent to this problem, or rewriting the series in this way. And ask yourself, how can I rewrite this value that has a repeating decimal? How can I rewrite it so that it is an infinite geometric series? So go ahead and check my solutions in Google Classroom for the answer to that question, but I highly, highly encourage you to try it on your own first.